Welcome to Frank Stajano Explains and the Formal Languages part of the Discrete Mathematics course at Cambridge. Last time I introduced deterministic finite automata and then I added various generalizations including non-determinism and epsilon transitions. Obviously, every deterministic finite automaton is also a non-deterministic finite automaton with epsilon transitions, simply one in which we do not make use of the extra freedoms of non-determinism and epsilon transitions. So the class of NFA-epsilon is obviously a superset of the class of DFA. But the remarkable and perhaps unexpected revelation is that the NFA-epsilon is not strictly more expressive than the DFA. Indeed, for every NFA-epsilon, it is possible to build a DFA that recognizes exactly the same set of strings. And I'm going to show you how. This is pretty cool. If you like this stuff, please say so by clicking the like button. Even though it's clear that every DFA is also an NFA, because you just specialize the transition relation to be a function. And it is clear that every NFA is also an NFA-epsilon, because you just specialize the empty transitions not to exist. It looks like we are getting towards more general things, but they are not any more general, because it is also the case that you can show the equivalence between an NFA-epsilon and a DFA that you started with. So all these things have the same expressive power in the sense that the language you can describe with any of them can be described with any other of them. So to do that, since the transition from DFA to NFA is obvious, and the transition from NFA to NFA epsilon is obvious, we are going to show the difficult one, which is that NFA epsilon is equivalent to DFA, and then by going around this loop you can prove any other equivalence you like. So to prove that you can build an DFA that will be recognizing exactly the same language as any given NFA epsilon, we use what is known as the subset construction, which is where we ended last time. The subset construction is so called because you build one state for the DFA for every possible subset of the NFA. So if the NFA epsilon has n states, then you will end up with 2 to the n states in the DFA. And this slide here shows you an NFA epsilon called M, which has these 3 states, and a DFA called PM, which has these 8 states that you see over here, which are all the possible subsets of the set of states of the NFA epsilon, which is Q0, Q1, and Q2. So what I'm going to do next, and what occupies the next 3 slides, 60, 61, and 62, is the kind of derivation that is very easy when someone else does it. And when you have a blank sheet and you have to do it yourself, I thought it was so obvious, but where do I start now? And in order to be able to reduce this thing yourself, it is crucial that you have at your fingertips the definition of the NFA, the definition of the DFA, and the definition of this particular DFA that's constructed from the NFA. If you're not able to reconstruct these on your own without looking them up, you don't have to memorize it. Memorizing doesn't help you. If you cannot work them out, like saying the formula in your own words, there's no hope for you to be able to work through that theorem. Please close the door as you come in. So the NFA epsilon was defined as a tuple containing the following elements. Let me just move this slightly out of the way. I can get rid of this. So the NFA epsilon was M was defined as a tuple with, first of all, a set of states. Then it had an input alphabet. So the set of states was anything you like, provided it was finite. The input alphabet was anything you like, provided it was finite. Then it had a transition function called, transition relation called delta, which was any subset of tuples of the set Q, Cartesian product sigma, Cartesian product Q. So any tuples in here were fair game for this delta. And then it had an S, which was one of the states, designated as the starting state. And then it had a F, which was a subset of the states, which was the set of the accepting states. And then it had a T, which was the empty, the epsilon transitions. So it was a subset of the relation between nodes in Q. So these 5 items in here, or 6 is it by now? Q, sigma, delta, small s, big F, and big T. These 6 things are what defines my NFA-epsilon, called M. And the DFA was the same, except that the big delta was instead a small delta, because it was a function from delta was a function from Q Cartesian sigma into Q, which had one and only one value for each pair of Q and sigma elements. And then there was no T relation. So this was the DFA. First line, the NFA-epsilon, second line, the DFA. And the way that I construct my specific DFA called PM is that the Q of the PM, we call it Q prime, is going to be what? We just said the set of all possible subsets of elements in Q. So the power set of Q, which is equal to S such that S is a subset of Q. Then the sigma for the DFA is the same as the sigma for the NFA-epsilon. The delta function for this DFA, what's it going to be? It's going to be a function that from any of these states sends me back into one of these states, depending on what the NFA-epsilon was doing. So if I am in this state over here, Q0, Q2, what did the NFA-epsilon do? Well, if I was in Q0 and I received a B, if I was in Q0 and I receive a B, where does the NFA-epsilon take me? Well, there's no arrow going out of Q0 with a B, so it looks like I'm stuck. However, there's an epsilon transition here, so I might just well explore this and see if I go here, well, there's an arrow with a B, and it sends me to Q2. So it is the case that from Q0, the string epsilon B sends me to Q2. Therefore, there is a transition in the NFA-epsilon that says Q0 B Q2, including some epsilon in here. I mean, I have this thing and I can drop it, so I don't care. So that's as far as Q0 receiving a B goes. What about, I said I was looking at this, I think. If I am in Q2 in my NFA-epsilon and I receive an A, what happens? Well, there's no arrow that says A here, so I don't know. And there's no epsilon transition taking me anywhere from here. So there's nothing else I can do from Q2. So it means if I am in either of these states in the original machine and I receive a B, well, one way or another, what will happen is that I might go into this Q2. So this is why the entry in this place has the set Q2. But if these various things had taken me different places, then I would have listed all the places I get to with that input. And this is why, for example, if Q0 is my starting state and I receive an A, then with an A I go into Q0, but I could also go into Q0 and then have an epsilon transition takes me to Q2, or I could go into Q0, have an epsilon transition takes me to Q1, or I could first have an epsilon transition and then in Q1 have an A that takes me to Q1. So I can, from Q0, if I get an A, there are paths labeled with A and as many epsilons as needed that take me to Q0, Q1, and Q2. And this is why the entry here says Q0, if you get an A, you can get into any of these in the NFA, and therefore you get into this state, which combines all of them in the DFA called PM. So if I were to write the definition of delta for my PM, what should I write? You must be able to write this yourself without looking it up. Otherwise, there's no hope for you to do the theorem. And what you would be writing is that the delta from a state S, which is going to be a subset of the states of the NFA, an input symbol A is going to be, well, as a type, it has to be an element in Q prime, which means it's a subset of states. So it has to be a set of states, Q prime. I'm going to call them Q prime, thinking that I have some transition from Q to Q prime in the NFA-epsilon, goodbye, labeled by A. And so I'm going to take the set of all the Q primes such that there exists one of these. So all the Q primes that are in the set Q, such that there exists some Q in my set that I started from, such that Q A Q prime is a member of my delta, which is the same as saying that there exists one of these, a transition from Q to Q prime labeled with the string A. So this is the set of all these Q primes is the outcome of applying delta to the starting set S with the input symbol A. And what's my starting state for the PM going to be? The starting state for the PM is going to be the starting state for the NFA, NFA-epsilon, which was called S, and anything I can reach from that through epsilon transition. So in this machine, the starting state is Q0, but I can get to Q1 for free. I can get to Q2 for free. So the starting state of my machine is going to be Q0, Q1, Q2 as the state of all the things I can spread to without having taken any input symbols. So this is going to be my S prime for my PM. S prime is going to be this. So formally, S prime would be S prime would be the set of Q prime in Q such that S Q prime is a couple in the T relation, or equivalently that there exists an S to Q prime epsilon transition in the original machine. You with me? Not if I'm making sense. Right. And finally, our set of accepting states for the DFA PM is going to be any of these subsets that contains at least one accepting state for the original machine. This means when I'm in the original NFA machine, which is non-deterministic and has many snakes going around and doing things in parallel, if at any point I get to an accepting state, that's good. So if I'm in a subset that contains an accepting state, well, Q0, Q1 does not contain an accepting state. Too bad. Q0, Q2, that's great. Q0 is not an accepting state, but Q2 is good. You might get to the Q2. That's great. So the F prime, the accepting states for my PM, is going to be a set of subsets, and it's going to be the subsets that contain an accepting state of the original machine. So it's going to be the set of S's which are part of Q prime, the original set of subsets, such that the intersection with the accepting states of the original machine is not empty. So if you have these things available at your fingertips, then you can start working with this, understanding how it behaves, and then even proving the next two halves of the theorem that shows that this machine on the left and this machine on the right recognize exactly the same language. It would be a good idea for you to visualize this machine in the same way as this one by drawing these 8 states as blobs and drawing these things as transitions between those blobs. I have so much to go through today that I don't suggest we do that together, but I had prepared this at home, and if I can get it out, it's somewhere hidden under this junk. Yeah, I had something like this. I've overwritten it with all these wonderful definitions now, but let me try to get to a situation where you can see everything. So this is these 8 states are represented as 8 yellow sausages, and the sausages are placed in this configuration so as to map these things. So when the sausage here has empty set, it means it contains none of these. This 0 means it contains this Q0. 1 means contains this Q1. 2 contains this Q2, and so on. So these are the 8 possible subsets of these 3 states in here. And anytime there is a transition in this table, then I put a transition arrow in here. So for example, from Q0, Q1, which is 0, 1, it's this sausage. If I get an A, I go to Q0, Q1, Q2, which is this other sausage. So there's an arrow that has an A and goes from this one to this one. Similarly, if I got a B, I would go to Q2, which is this other one. And so you draw yourself this thing. And then you can play around with an input string saying, well, I got the input string A, B, B, A, B, A. And what happens to my machines? You should imagine these things as like pinball machines that have little lights. Every state has a light. And when you are in that state, the light goes on. And in the machine, which is non-deterministic, several states can be on at once. And in one that is deterministic, only one state will be on at once. Exactly one state will be on. And so if you start, you always start in the starting state, hence the name. I think that I will now need to bring this to the front, bring this other thing to the front, and bring this other thing also to the front in order for me to be able to move it to here and say this is the highlight of my start state. And this, my start state, we said earlier, had to be Q0, Q1, Q2. So this has to be my start state. I should put an arrow in green to say this is the start state. And then if I receive an A, when I receive this A, this machine over here with an A goes to Q0, can go also epsilon transition to Q2, can also go epsilon transition to Q1. So in fact, this machine will end up lighting up all of these. And so this machine will, from A, go to appropriately itself, which is also what we have here, Q0, Q1, Q2, with an A, I go here. So if you work a bit with those two machines and you execute this in parallel on both, then you should be seeing what happens with AB, BA, BA. Is it accepted or not? We had a list. We should make a list of the accepting states for this one. It should be all the states that include Q2. So the accepting states for my DFA PM would be this one, this one, this one, and this one. You can play around, see where you are, and it should be completely synchronous, what happens here and what happens here, and you should end up in a state, in a combination of states here, the equivalent state over there, and you should then tell if it's accepting or not.